You're now listening to Smart People You Meet at Parties, a podcast from Entrepreneur First, the world's leading talent investor. My name is Bernadette. I'm the General Manager of Entrepreneur First Singapore, and I'm privileged to speak with some of the sharpest minds in Southeast Asia's startup ecosystem. This podcast gives you a behind-the-scenes listen into the everyday conversations we have at EF with founders, investors, and thought leaders in deep tech. For today's episode, we're joined by Tommaso Demarie, CEO and co-founder of Entropica Labs. Entropica creates algorithms, software tools, methods, and models to make quantum computers useful. Tommaso breaks down the mind-bending world of quantum computing and shares how we got from bits to qubits. Thanks for listening, and I hope you enjoy the conversation as much as I did. Hi, everyone. Thanks for dialing into Spy Maps. This is our third episode. I'm very happy to be joined by Tommaso, who is the CEO of Entropica Labs, which has just made a very exciting announcement today. Tommaso, I'll pass over to you to share a little bit more about what the announcement was and also what Entropica Labs does.
Sure. Well, thanks, Bernadette. Very nice to be here. Let's start with the announcement since it's kind of fresh news for the day. There was also an interesting coincidence that just happened this morning. So it's quite exciting because as a company, we reach our first big milestone, I guess that's fair to say, which is closing the seed investment round. So this morning we made public that we did so, which is great. We raised 2.6 Singapore million, which is quite a relevant amount of money. And especially in the current situation, this is really going to take us a long way. And we're going to use the money to build the technology, to further develop the tech, and also to grow the team here in Singapore. And to say a bit more about us as a company. So Entropica is a company based here, Singapore. We build software for quantum computers, which I believe is what we are going to discuss later with Bernadette. Today is a very relevant technology, I would say, because lately we have seen great progress in the field of quantum computation. We have quantum computers on the cloud, and we as a company are very much intrigued in understanding what we can do with these machines. And even before we make it to that point, we want to understand how we can code and really push the machines to the limit. Or maybe I can summarize it by saying, or by state our mission, which is doing the best with quantum computers today. So to summarize, because I don't want to talk too much already at the beginning, to summarize, we are a Singapore-based company working on quantum software development.
That gives me something interesting to springboard off. So today I am going to try and learn about quantum computing from Tommaso. This will be interesting from both Tommaso and myself. I have a background in political science and French. That's what I studied. And on his end, Tommaso, can you share a little bit about what you studied?
For sure. Maybe unsurprisingly, I've studied physics. So my background is quantum physics. I have a PhD in quantum information theory from Macquarie University in Australia. Although I'm from Italy originally, I moved to Australia in 2010. Did my PhD there and then moved to Singapore in 2014, where I continued working in what is called quantum information theory, which, if you like, is the branch of physics, I was going to say, that sits above quantum computing. Maybe it's a bit more nuanced than that, but it's fine for a conversation. So I spent 4 more years in Singapore working as a postdoc in quantum information theory just before joining EF. So my background is very much hardcore science, one might say, although I also have to admit that in the last few years, I've been really enjoying thinking about these problems from a more business / holistic / practical perspective as my role, commands and demands.
Great. So maybe in a nutshell, Tommaso, where we can start is, can you explain what quantum computing does? And if I'm not mistaken, is quantum computing the same or different to supercomputing?
Okay. So keep the second part of the question there for a second. We'll get back to that. So even before we start with that, I think it's very important to understand what computing is. So when we speak about computing today, which is something that everyone, I would say, is familiar with, what it really means is that we are processing information. So you have some information, which could be, our images or our voice right now. It could be a text message. It could be a photo. It could be, music. It could be a document. Could be data in any form. So you have information and you want to process it for whatever reason. When you process information, we can say that you're computing something, okay? And I'm saying that because it's very important to start differentiating between what I will call classical computing or conventional computing and quantum computing, so that we can start moving closer to defining what that is. So basically, conventional computing is everything we are familiar with. When you use your phone, when you use your laptop, even when you use a supercomputer on the cloud, today you're performing what we will call a classical computation. The computation involves classical information, so a sequence of zeros and ones of bits. And however you process it, you could use a CPU, you could use a GPU, a TPU, an FPGA. Doesn't really matter if these names don't mean anything just yet. Or whatever means you use, you start with a string of classical bits. You might change the bits throughout the computation, but you will still maintain a string of classical bits, and you end with another string of classical bits. That is a classical computation. And everything I just described follows the laws of classical physics. It doesn't mean it's simple, it just means it's classical. And it has certain limits of what it can do. Things get very interesting when you add the word quantum to that, which means that you don't have to deal anymore just with classical information, but you can start playing with what we call, again, it's not very evocative maybe, but what we call quantum information, which means that the structure of the information itself changes. And you deal with something called qubit or quantum bit, which maybe most of the listeners have heard of because it is a concept that is thrown around a lot in the news lately. Without being too scientific or without, playing the part of the physicist now, a quantum bit means that you have certain features that are not present when you deal with a classical or conventional bit. It also means that when you perform a quantum computation, you can take advantage of these features like entanglement or superposition or interference.
Can we pause there? Can you tell us, so I will be honest, and I tried to read some articles about this to feel more educated before I spoke with you. And I got tripped up on these words. So can you tell me what entanglement is or superpositioning? So what I'm hearing is that classical computing is made up of bits, zeros and ones, which is different from qubits and superpositioning and entanglement. Can you tell me more about that?
Okay, so I'll try to give you an analogy. I like analogies a lot. I'll try to give you an analogy. So imagine planet Earth, right? Planet Earth has a South Pole and a North Pole. Mm-hmm. Imagine you're traveling on the planet and you want to encode a bit depending on your presence or your position on the planet. If you were to encode a classical bit, that would mean that you can limit your presence only to the South or to the North Pole exactly.
Okay.
And if you are at the South Pole, you're encoding a 0. If you're at the North Pole, you're encoding a 1. And that's it. There's nothing else you can do. But if you are trying to encode a quantum bit, all of a sudden you can travel anywhere you want on the position of the planet, anywhere on the surface, actually even inside, but let's not make it too complicated. You can be anywhere on the surface of the planet. If you are at the South or the North Pole, you are again just encoding a classical bit using a quantum bit, which you can do. But if you are anywhere else on the surface, you are in a superposition of the 0 and 1 state, which really means, loosely said, that you are somewhere in between these two states. And you can immediately see intuitively that you have much more computational space that you can use. Because in the classical bit, you're limited. You can only be 0, 1. But if you can travel anywhere on the planet, you can do more. And this is the concept of superposition.
How does that play out practically? So for example, if you could give me an example of what that actually looks like in practice, maybe how Entropica uses it or how you've used it previously to enable you to do something you otherwise weren't able to do.
Sure. Right. So practically, let me start with the practical part. So there are different ways you can actually build something like that in nature. You can either use a natural atom, so you can, if you have enough architecture in your hands, you can build a machine that traps ions, which are charged atoms.
Yeah.
And if you can trap these atoms, you can use certain characteristics of these atoms to encode your 0 and 1s. You can kind of think that if the atom is oriented in a certain way, it's 0. If it's oriented in another way, it's a 1. If it's oriented in between, it's a superposition of the two. Very loosely said. And if you want to do something non-trivial, well, it's still not going to give you any real advantage, but it's a non-trivial exercise. You can think of the following very tiny experiment that you could do. If you have a bit, is either 0 or 1. And if you observe the bit, it's not going to change. It remains either 0 or 1. But if you have a quantum bit, you put it in a superposition, in an equal superposition of 0 and 1, and then you observe it. Depending on the way you observe it, it's going to collapse either in a 0 or in a 1 state. So you cannot really observe the superposition. It kind of always goes back to what we call a classical state. And part of that is because we are classical beings and we are not built, as far as we know, we don't have a natural way to interact with quantum states. So everything we do with quantum states has to go back to a classical state. And to your point, the moment you do this observation, you're basically extracting randomness from this quantum bit. Because when it collapses to 0, 1, you cannot predict if it's going to, well, you know the probability. Maybe with 50% it's going to be a 0, with 50% it's going to be a 1. But you cannot predict if it's going to be a 0 or 1 with certainty. So you're creating randomness by measuring the qubits. And it might not be immediately obvious why this is useful, but it's actually very useful, for example, if you're trying to build cryptographic protocols. It's not something that we do. But to make the whole statement more concrete, you can think of a quantum computer, or one of the many ways you can think of a quantum computer is a machine that naturally produces randomness, which can then be used for certain tasks. You can't do that with a classical computer. If any software engineer is listening to us, they will all know that they have to deal with pseudo-randomness when they build, for example, a Monte Carlo algorithm, which means that they are simulating randomness. With a quantum computer, you don't have to deal with that. You can produce randomness, pure randomness, naturally.
And I guess that's advantageous in the way then simulations can be stress tested, or potentially to see how they interact in different scenarios or how things play out.
Potentially, yes. We are starting to enter a little bit this more speculative aspect of it, because the reality is that no one has proven that this is the case, but there are proposals on how you could use these features of quantum computing to improve, for example, Monte Carlo simulations, something which is called quantum Monte Carlo.
I'm always tempted to kind of jump into the very practical applications of things because that's what it's easier for me to wrap my head around.
Sure.
But in the interest of kind of trying to pursue a more interrogative line of questioning, I would love to hear more about entanglement then. So that is super positioning. How is entanglement related to this or different to this?
So let me give you another example. Let's see if the analogy works. So imagine that you and I are going to get a gift for our birthdays, right? I'm not sure when is your birthday, but let's imagine that we were born on the same day. And, the EF team is going to give us a gift each.
Be nice.
In a class, that would be nice, right? So they want us to get a gift. And in a classical world, what they have to do, they have to decide in advance what the gift is. You put the gift in the box, give the box to us, and it doesn't matter what we do. It doesn't matter, it doesn't matter if we tell each other, oh, maybe we can open the box in a certain way, and maybe you can open the box in a different way, and then might change the gift inside. No, whatever they put it inside in a classical world is going to stay exactly the same. We open the box, nothing has changed. At most, what the EF team can do is to decide to put two equal gifts so that they create some correlation, because the EF team knows that the gifts are the same. So there is a correlation between the two, but there's nothing they can do to change them once they've given it to us. But in a quantum world, they could exploit entanglement, which means that you're creating a stronger form of correlations between the content of the boxes. And as long as we don't open the boxes, there is a little bit of randomness involved, which we might be able to use it for our own advantage. And to make it a bit more practical, what it means is that, let me ask you this question. What is it you would like to receive for your birthday?
Right now, I'd really like to travel. That is really
okay. Sure. So would I. But something a bit more concrete that you can actually put in a box.
What I'd like a book.
A
Trying
book,
to do
okay.
yeah.
Good. So let's pick two things, one book and another one. Give me another gift that you would like to receive.
You know what? I have been quarantining without a pet, and I see a lot of my teammates have pets. I would like a pet.
Okay, so let's say, are you okay with a rabbit, hamster?
You know what? To be honest, I'm not. I've had rabbits before, and they're really nasty. I would either like a puppy or a kitten. Just to be honest.
Fine. Let's get the puppy.
All the out there.
Let's get the puppy. We're going to make a safe experiment. The puppy's going to survive being inside the box, so no one gets angry for this sort of experiment. Okay, so what the EF team does, they prepare this superposition of book puppy plus book puppy. Oh, actually, it's better to say book plus puppy puppy, okay? Which means that inside our box, we have, and now I'll say something that will infuriate all the physicists out there, we have at the same time a book and a puppy, depending on how we are going to observe the state inside. And in practice, what it means is that if I open it and I find inside a book, I immediately know that you're also going to find a book inside your box, even if you have not opened it yet.
Okay.
But if I open it and I find a puppy, I also know that you're going to find a puppy. And this is something that you cannot do classically, right? Either there's a book or there's a puppy, there's nothing in between. Or you can change things later on, right? But when you have entanglement, you're creating these correlations that are stronger than classical correlations that can give effect to some pretty funky stuff. Of course, you're not going to be able to entangle a book with a puppy. It's not something that, as far as we know, you can do in practice.
Mm-hmm.
But you can entangle the state of qubits.
So this is just to play it back in a very much more layperson way. It means that whatever your outcome is, you can correlate that such that it triggers the same outcome for me.
Let me be pedantic. I love being pedantic. What it means is that they're actually correlated to begin with, depending on the preparation. And the moment I acquire some information about the state, there is also telling me something about what you have or what you might have inside your box in this case. I cannot really communicate to you because of something called no signaling principle, but that is really maybe outside of the discussion. The point is I'm creating, with entanglement, you can create very strong correlations that, as far as we know, cannot be created in a classical world.
Interesting. Very interesting.
It's fantastic.
Okay.
And the funny thing is that, again, as far as we know, these correlations don't depend on the distance. So even if you move to the other side of the galaxy, that will still hold.
Very fascinating. So Tommaso, I know we're running up on time now, and I'm just curious to hear your perspective then on what you think the future of quantum looks like. Thank you for my very abridged crash course. I have two more questions for you. That's the first one, which is, where do you think this goes practically? What are the use cases you see it being able to materially make things better or different for the world?
So I'll give you a very disappointing answer, I think. I try to be as... So I'm always, let me say it this way, I'm always a little bit uncomfortable to speak about use cases and applications of quantum computing because it's very speculative in nature. And I could tell you anything, right? I mean, I can tell you that quantum computers are going to solve climate change. Yeah, maybe. But I just don't think these are very meaningful statements because they're speculative. I think what is much more interesting is that by learning more about quantum computers and by learning more about the fundamental limits of what computing even means, well, we are doing something very important, right? We are pushing the boundaries of computation. We are learning how to control what you might very well call more computing power that is available today. And then you can try to extrapolate, right? I mean, today, everything we do is based on processing, on information processing, absolutely everything. This call is based on information processing. Everything you do from the moment you wake up to the moment you go to sleep is based on information processing, pretty much. Which means that we live in a society for the, for good or bad, or for the best or the worst, I don't know. I'm not going to make a moral judgment or moral statement, but we live in a society that is grounded on a need, on a never-ending need for computing power. And if quantum computing can provide that, I think it also offers a way to start thinking how to solve really hard problems. And now I'm entering the speculative part of the answer. Really important problems in chemistry, in material science, in machine learning, in optimization. And then the sky is the limit. In the same way that people didn't really have any clue about use cases for classical computers in the 40s, I think people, to be fair with you, don't have a real clue about use cases for quantum computers. It doesn't matter because we will find them. The moment you have the machines and the moment the machines work, you will find use cases. And if you want an interesting, maybe a bit of parallelism between the past and today, people started to build computers for a few reasons, actually, for physics simulation and for cryptography, mostly. And this was unfortunately motivated by the war, right? The Second World War. And the very beginning of quantum computation was motivated by simulating physics and cryptography. So there is nothing new. Yeah, there is absolutely nothing new. And to me, this is fascinating because we are, in a way, looping back to where classical computing was in the 40s, in the 50s, in the 60s. And that's fine. We can imagine use cases of the technology because we don't have the technology just yet. In the same way that I believe you and I weren't able to imagine use cases of our cell phone beyond being a phone when we were kids because we didn't have it in our hands. Doesn't matter. They have endless use cases.
Yeah. Oh. Very interesting. Last question for you then. You mentioned you're developing software for quantum computing at Entropica. Yes. What types of software are you trying to build, and what will that serve in the quantum computing space?
Yeah, good question. So we are very much at the, I would call it enabling layer. If you think you have the hardware at the bottom, you have the applications at the top. In the middle, you have all that software tools and methods and algorithms that are needed to make sure that you can actually use the machines to do something or to solve useful problems. To give an example, we built and released what we call the Entropica QAOA, which is a software package written in Python that allows people to deploy a quantum approximate optimization algorithm workflow on the Rigetti computing quantum cloud systems. And this is really a very basic, not basic meaning that is simple, but basic meaning something that works very closely to the hardware. And it's the kind of software that today we're not really familiar anymore in classical computing because we have a lot of layers of abstraction available, which means that developers usually don't need to go so deep into the, well, what we call the software stack for classical computing because you can abstract all of those concepts away and use high-level languages to code. In quantum computing, we don't have the luxury just yet. So we need to kind of go back and look at to look at all the bits and pieces of software and tools that are needed so that even we can actually control and use these machines simply to test them. I'm not even thinking about applications just yet, simply to benchmark them, simply to understand how you can take a problem which might be common to you and encode it in a way that is amenable to a quantum computer. So I haven't given you a single sentence, I've given you bits and pieces of what we actually do. I hope that gives a good idea.
I think I will need a follow-up chat, but I think it's a good start and I know we're up on time. So thank you so much, Tommaso. I really appreciate you trying to educate this recovering art student on what
Oh,
quantum
come
computing
on. Don't say that. But it was my pleasure.
Thanks for tuning in. If you enjoyed today's episode and are interested in founding your own company, apply via joinef.com. We'll help you find a co-founder, develop ideas, and launch your company from scratch. And we'll invest in you from day one. Applications are now open for our cohorts in Singapore, Bangalore, London, Paris, Berlin, and Toronto. To listen to more episodes of Spy Maps, visit joinef.com. And thanks for listening.